So this is EE610, lecture 3, and we have been analyzing a nonlinear two-port network. Let's say the port voltages are V1 and V2. We assume that the currents were I1 and I2. Then I1 is related to both V1 and V2 through some nonlinear function f. Similarly, I2 is related to both V1 and V2 through some nonlinear function, a different nonlinear function which we called as g. Now, if I make a small change in V1 and correspondingly, let's say I make another small change in V2, then I expect to see some small changes in I1 and I2. Some incremental changes around the quiescent operating point. And then we saw that even if your network is nonlinear, it is possible to relate these incremental changes in V1 to the incremental changes in I1 and I2 using linear equations. Right? And we wrote this in the format of a admittance matrix. So we had I1, I2 being equal to Y11, Y12, Y21, Y22 into V1, V2, where what is this matrix called as? This is the incremental Y parameter matrix or incremental Y matrix. These are incremental Y parameters. And you need to derive these incremental parameters at the operating points. Okay. What was the definition for Y11? That will be equal to dou f by dou V1 at the operating point. Similarly, Y12 is dou f by dou V2, Y21 is dou g by dou V2, etc. etc. Okay. Now, let me ask you a question. Let's say I take you to a lab and I give you a black box. I give you a breadboard onto which you can plug this black box. It has two ports with four terminals. Okay, and I give you enough current sources, voltage sources, enough measuring equipment. And I ask you to tell me what its Y11 is. How would you go about measuring the Y11? So I have given you a network with two ports. I've given you all the voltage sources, current sources, any measuring instrument you need. So you'll short the output. So on what basis are you telling me this? Based on this expression, I1 equal to plus into V2, right? So it looks like if I make V2 equal to 0 and then I take I1 by V1, I should get Y11, right? So is this all I have to do or am I missing something? Why DC source is needed? So whenever I ask you to measure a Y11 and tell me the value, you should immediately ask me at what operating point. Because your Y11 is a function of the bias points. Okay. So now let's say I tell you I want Y11 at some V1 0 and V2 0. So now how would you change your experiment? Is that clear? The question is clear? I first have to make sure the network is biased at V1 0 and V2 0. Right? So I first connect the biasing voltages. Draw this a little big. So on the input side, I will first connect V1 0. On the output side, I will connect V2 0. Right? Once I make this full connection, I will have some I10 flowing through this, some bias current flowing into the second port, which I'll call as I20. So these are now my operating points or the quiescent voltages and currents. Okay. Now on top of this, I introduce my incremental V1. So in series with this, I can connect a small V1 source. Once I connect the V1 source, I would expect the current to change. Do I expect I2 to change? Yes? No? Why yes? So if you say no, why no? I2 is a function of V1 also, right? So you will see some small I2 here. Okay. So now what is Y11? Whatever is the small I1 you get here divided by this V1. Now how would you measure the small I1 separately? What will you short? You will short V10. The moment you short V10, the biasing point is now different. Instead of biasing at V10, V20, moment you remove V10, you have biased it at 0, V20. It's a different biasing point. Your I1 value, the incremental I1 value is going to be different. Right. So in the first setup, you would measure I10. In the second setup, you measure I10 plus I1. Right? Simply make sure that the emitter you are using for measuring has good resolution to capture I1 also. Then you take the difference and you have the incremental I1. Is that clear? There is a doubt? You can ask if what part is confusing. So in the first setup, I connect only V10, V20. Right? I have this circuit. And then I measure the current through this path. Let me call this as my I measurement A. And we expect this to be I10. Then I connect the incremental voltage source V1. I expect this to change by I1. This changes by I2. Then I take my second measurement. Let's say I mesh B. This will be equal to I10 plus small I1. Now, the small I1 can be obtained by taking the difference between the two. Right? And in this setup, the incremental V2 is 0. Therefore, if you do I1 by V1, you will get Y11. Okay. Now, let's say I want to measure Y12. Can I use the same setup or do I need to change something? What is the expression for I2? Right? So now to measure Y12, what change do you think I need to do? I have to remove V1 here and connect V2 here. Right? So before I change the network for measuring Y12, do you think I can measure any other parameter based on the current network? Y21, right? So what is Y21? That will be equal to I2 divided by V1, right? I2 can be obtained from here, V1 is here. Now to do Y12, of course I will have to change this network. This gets shorted and I add the incremental voltage source on this side. Right? And I repeat the same procedure. Once I add V2 here, I would expect this current to change by some quantity. This current will also change by a different quantity. And you can look at what is I1 by V2 and I2 by V2 to identify Y12 and Y2. This is clear? So now if I give you any new device, you would be able to measure the Y parameters at a given operating point. If I ask you to plot a graph for these Y parameters, you will keep changing the operating point and keep repeating these measurements. Okay. So then let's go back to our analysis for the incremental Y parameters for an amplifier. Do you remember our wish list for the amplifier? What all did we conclude? So we are working with a 2-port, 3-terminal network. We are looking at the incremental gain. What else? It should be independent of both RL as well as the source resistance, and we wanted a large gain. So we took some incremental Y parameter network. I'll write it as GS. And connected some voltage source Vs to it. And then we also connected a resistor with conductance value GL to it. How did we replace this network as? This was Y11. This is Y12 times V2. This is Y21 times V1. And this was Y22. This is a common terminal. Okay. And we did some quick simplifications and replaced this GL with Y22 plus GL. And we also did Norton equivalent to replace VSGS as a current source with a GS in parallel to Y11. Okay. Do you remember the gain equation? So this is your V out. This is V1. V out by V in was minus Y21 GS divided by, this will be Y22 plus GL into Y11 plus GS minus Y12 into Y21. So we got this equation. Then we figured out that if your Y12 into Y21 was equal to this factor, your system can become unstable. You'll get infinite gain, which means there is an output even when your input is 0. Right? So we did not want this to happen. So as a precautionary measure, we made the complete second factor to be equal to 0. And we did this by making sure our Y12 was equal to 0. Right? So we made Y12 equal to 0, meaning now this part of the circuit is not there. Right? So now there is no feedback from the output to V1. If there is a change in V out, that is not affecting our V1 in any manner. Okay. Now, I also want to make sure that this gain is independent of the source resistance, GS. What can I do? Remember, GL and GS are not in our hands. Right? We can only play with the remaining parameters. Y11 can be? Should it be very big or? It has to be 0. Right? So if I make Y11 to be equal to 0, then this GS and GS will cancel each other. Okay? Now again, let's look at the circuit and understand what effect it has. I am making Y11 equal to 0, which means this resistance is becoming infinite. That means I am open circuiting this portion of the circuit. Okay. So now whatever is the Vs, because no current is flowing through GS, the same value is going to appear as V1. Earlier, in the presence of a finite y11, the value of V1 was going to be smaller than Vs, right? And you were losing out on some gain in this portion. Now, by removing y11, I am able to ensure that the complete Vs is appearing as V1. Okay. So, how does my equation look now? So, this becomes minus y21 divided by y22 plus GL. Now, what should I do to y22? Y22 also 0. Why? We want to make our gain to be very large. So, I am reducing the denominator to as small a value as possible. So, this gives me minus y21 divided by GL. Right? And what is the reasoning here? I am completely removing the y22 part. So, all of the current flowing in this path now has to flow through GL. Now, instead, if I had two resistors there, let's say I had y22 and I had a separate GL, the current that is being provided by this y21 V1 is going to split between y22 and GL. So, the current flowing into the load is going to reduce, which means that the power being delivered to the load is also going to reduce. Right? So, by removing y22, we have sorted out that problem. Maximum current is now getting delivered into your load resistance. Now, we are at the last stage. What comment can you make about y21? Make it as large as possible. Okay. So, what is our conclusion? We want y11 to be equal to 0, y12 to be equal to 0, y21 has to be as large as possible, and y22 to be equal to 0. Right? And our final gain is simply minus y21 divided by GL. Did we achieve all of our items in the wish list? No, gain is still dependent on GL. This is life. You can't achieve all the items in your wish list. We just have to deal with it. Okay. So now our incremental Y matrix looks like this. You have 0, 0 and 0 here and a very large value here. That's it. So if we can find a device that can give you an incremental Y-parameter network like this, that is a really good candidate to start designing amplifiers. Okay, so before we get to one such device, let's also quickly look at what comments we can make about the large signal properties of this device, right, of this Y-parameter network. So we are basically going to look at how this I1 as a function of V1, V2 and I2 as a function of V1, V2 is supposed to look like. Right? And to do this, we will simply rely on the 4 graphs that we dealt with in the previous class. So we will look at I1 versus V1. I1 versus V2. I2 versus V1 and I2 versus V2. Right? So let's make use of the information that Y11 equal to 0. What does it mean? I1 versus V1 has to be constant, right? I1 equal to 0 means that dou F by dou V1 is equal to 0. Right? So you expect to see some constant current here. Right? This is of course for some constant value of V2. Let me call it as V2A. Right? At a particular bias point. can you quickly tell me how the graph will look in I1 versus V2? So I1 versus V2, if I calculate the slope of I1 versus V2, what do I get? Y12 is 0, right? So Y12 being 0 tells you that if I do take a derivative of dou I1 versus dou V2, it has to be 0, right? So that means I would expect to see a flat line here. This is of course true for some bias point of V1. Now looking at both the graphs, can you tell me what I should expect to see here if I change my V2 to some V2B? Do I expect to see a separate line? Do I expect to see something like this? Or do I expect to see a different property? I would expect to see a second line. Okay, let's see if that answer is correct, right? So if on this figure, if I go from V2A to V2B, does my I1 change? It doesn't change, right? So now here, for the same V1A, if I go from V2A to V2B, should my I1 change? It shouldn't change, right? So I wouldn't get a second line here. It's just a single flat line. Is that clear to everyone? So similarly, if I go from V1A to V2B, what do I expect to see? Unchanged. You are still on the same line. Okay, good. Now, I2 versus V1, what plot should this give you? Like, what parameter is this graph giving you? Y21, right? And how do we want our Y21 to be? As large as possible. So it has to be some curve where if I take the slope of it, it is very high. That's all. Right? So I have roughly drawn a curve like this. What about I2 versus V2? So we know that Y22 equal to 0, which means this has to be a relatively flat value. Right? Now, yeah.
Not be a straight line because we want L of V2 to be 0, denominator to be 0. Ideally, it will be infinite. We want a large gain.
We want a large gain, right? So, which parameter are you talking about?
Denominator. We will make denominator 0. It will be like infinite. So, will it not be a straight line just for the x?
So, you want a line like this? So, if the gain is infinite, then it means that the output is independent of the input, right? We don't want the gain to be, we want the gain to be as large as possible.
Ideally, it should be straight. We take gain as infinite, ideally it should be straight.
So, we'll come back to this gain equal to infinity part in a little minute. And the reason is if gain is infinity, it can also mean that you get an output even without an input. We want the output to be some scaled version of the input. So you need the slope to be very, very large, the limit to which is it being infinity with a straight line, but infinity is a slightly tricky point. So we'll just say that we want the gain to be very large for. Okay. So now in this plot of I2 versus V2, let's say I plotted this for some V1A. If I go from V1A to V2A, do you expect to see a separate line or is it going to be at the same point? Separate line, right? Why? Because in this, if you go from V1A to V2A, you see that your current is changing. So similarly, you would expect to have a separate line for V1B here. This notation should have been V1A to V1B. Okay. And quickly comment on I2 versus V1. For different values of V2, do I see different curves? No, right? Because if you change your V2, your current is not changing, right? So even if you keep changing your V2 value here, you will still get the same outcome, right? So roughly, this is the sort of large signal characteristics we expect. Now, anything that is not small signal, we call it as large signal. That's all. So please quickly see if you have any questions. Feel free to discuss. So how many of you have seen a MOSFET before? Is there anyone who has not seen a MOSFET? You have not seen a MOSFET before, is it? No, have studied about a MOSFET. Theoretically know what a MOSFET is, know its IV characteristics. So you have not seen a physical MOSFET but have learned about MOSFETs, right? So if there is someone who has not gone through the theory of MOSFETs even once, please meet me after the class. I'll give you additional resources. But otherwise, our approach in learning with MOSFETs, especially the device part of the device physics of MOSFETs, is this. We'll not cover that in E16 because you're going to learn about that in your solid state circuits course, right? It will come towards the end of the course, but you're going to learn about it in a great detail. So instead of focusing on the device physics, we'll focus on the circuit aspects of it. And we'll treat the MOSFET as a black box for now, and I'll give you its IV characteristics. Okay. So our main aim is to compare the MOSFET to a 2-port 3-terminal device and see how the IV characteristics can match up to the large signal characteristics we have seen here. So this was my V1. I have current I1 flowing through this, current I2, this is V2. So we'll start with the NMOS. The symbol for NMOS is this. This terminal is called as the gate, represented using the letter G. This terminal is called as the drain, represented using D, and this is your source terminal. Right? The source terminal has this arrow as shown here. Right? Now, the terminal between gate and source is your terminal 1, where you apply V1 and see a current I1 flowing through this. Right? The terminal between drain and source is your V2, and the current flowing in is your I2. Now in practice, we don't keep calling these as I1, V1, I2, V2, etc. We call this based on the terminal notation for this particular device. So instead of I1, you have IG, or the gate current. Instead of V1, you call this as VGS. Right? The drain current, or the I2, is called as the drain current. You denote it as ID. Sometimes you also denote it as IDS. And your V2 is your drain to source voltage, or VDS. Okay. Let me quickly show you how the structure of the MOSFET looks like. So especially if you are dealing with an NMOS, you will have a P substrate on which you will have two N+ regions. Then you will have an oxide layer. On top of it, you will have a gate. So earlier this gate was fabricated using metal. So then you had a metal, oxide, and a semiconductor region. That is how this MOS came about to be. But now the gate is no longer created using a metal, it's done using polysilicon. But for historical reasons, we still call this as a MOS transistor. Okay. Now this is your gate terminal. This is your source terminal. Let's say this is your drain terminal. So for a MOSFET, the source and the drain terminal are very symmetric. You call one as source and the other as drain depending on the flow of the current or whichever is the higher potential. So for an NMOSFET, drain is always at a higher potential than the source. And your current always flows from drain to source. Right? So this terminology is a little confusing, right? Current is starting from drain and it is going towards the source. Why did that come out to be? Because the naming convention is not with respect to the current, but is with respect to the charge carriers. So for a NMOSFET, the charge carriers are electrons and they go from source and they drain at the drain. So that's how the source drain convention has come out to be. Now you generally also have a body terminal, that is basically to make sure that the P region is also biased correctly. So you take it out using a separate contact here. But for now, we will not worry about the body terminal. We will simply deal with a symbol which has gate, drain and source. So your VGS is connected like this. And you would typically ground your body and source together. For now, I'm grounding the body and source together so that it becomes easier to show you the VDS. And you can connect your VDS like this. Whenever you have enough voltage at VGS, a channel is formed underneath. On top of it, when you apply a sufficiently large VDS, you have the current flow going through it. Okay? I'll show you the IV models in a short while. But I also wanted to show you two particular dimensions for this device. So if I were looking at it from the top, so I have this N plus region which I have called as the source, and I have another N plus region which I have called as the drain, right? And the current is flowing from drain to source. Now this distance is what we call as the channel length, represented by the letter L. So this is the channel length. Okay? Now into the plane of the paper, right? This is your channel width or W. This is your W. So this much is enough for you to proceed with our calculations. Now let us try and figure out how your IG is related to, so this should be some function of VGS and VDS. Similarly, you would expect your drain current also to be some function of VGS and VDS. Okay. So let me give you this relationship. Your IG is equal to 0. That's it. Your gate current is equal to 0. This is of course true for low frequencies. But given that we are looking at large signal parameters where this IG is going to be your IG, VGS, VDS, etc. are going to be that initial point where you solve the network before you apply the incremental voltage source. These operating points are going to be DC, right? So frequency equal to 0. So this is a good enough approximation, right? So your IG is equal to 0. What did we want our IG to be actually? What did we want our I1 to be? We just wanted it to be a constant, not necessarily 0, right? But it is 0 and it is a constant 0, so we are happy. Now let's look at the expression for the drain current. This is divided into, the expression depends on the region of operation of this drain current. Or in other words, the region of operation of the MOSFET, or in other words, it depends on the values of the VGS and VDS you apply. So, your drain current is equal to 0 if the VGS you have applied is smaller than a voltage called as the threshold voltage. Okay. So this VTH is called as the threshold voltage. Now, in the examples that we are considering, we will assume that the threshold voltage for an NMOS transistor is positive. Right? This actually deals with a particular type of NMOS transistor called as enhancement type of transistors. There are a lot of varieties of transistors. You know about NMOS and PMOS, but even in NMOS and PMOS, you can have different flavors for these transistors, right? But we'll focus our attention on enhancement type NMOS transistor and PMOS transistor. With the idea being, if you know how to work with this, for any other device, you should be able to do the same thing, right? Repeat the same process of calculation, get the incremental network, and solve the rest. Okay, and this region is called as cutoff region. Right? Now, ID is equal to mu n COX W by L into VGS minus VTH into VDS minus VDS square by 2. When is this true? First, your transistor has to be on. It shouldn't be in cutoff. Therefore, your VGS has to be greater than VTH. On top of it, the VDS has to be lesser than VGS minus VTH. What is this region called as? This is called as linear or triode region. And finally, ID can be equal to mu n COX W by L into VGS minus VTH the whole square. When is this true? This is true in saturation region. In other words, the biasing conditions are the VGS has to be greater than VTH and the VDS has to be greater than VGS minus VTH. This is called as the saturation region. So the expression I have written is not complete. There is also a 1 plus lambda VDS here, right? But the lambda value tends to be very small typically. So for now, we'll consider only the rest of the expression. We'll introduce this lambda in a short while. Let me also quickly explain all the new terms that you are seeing in these expressions. What is mu n? So this is the mobility of the electron. COX. This is the gate oxide capacitance. Per unit area. So W and L I already explained. These are the dimensions of the channel. And the factor lambda is called as channel length modulation. Or CLM. For the initial part of the discussion, we are going to assume that lambda is equal to 0. So this factor, mu n COX into W by L, quickly tell me the dimension of this factor. Ampere per volt square, right? Is that obvious to you? So on LHS you have ampere, right? Which means this whole term has to have the dimension of ampere. Now this portion has the dimension of volt square. Therefore this should have dimensions of ampere per volt square. Okay? This is what we call as the current factor. And typically, though the unit is ampere per volt square, because the currents you're going to deal with will be in microamperes and milliamperes, you tend to represent this either in milliampere per volt square or microampere per volt square unit. Okay. Now, can you quickly do the plot for the large signal plot of equivalent of I1 versus V1, I1 versus V2, and I2 versus V1 and I2 versus V2. The IV characteristics are given to you. See if you are able to plot it. So your Ig is equal to 0. Therefore, the first two graphs are very easy to plot. Right? To give you a feel of numbers, I will plot this with certain parameter values. I'm going to assume that mu n COX W by L is 100 microampere per volt square. VTH is equal to 1 volt. I'll first start with ID versus VDS plot. So this is in volts, and let's say the current is given in microamperes. Okay, so if your VGS is lesser than 0, VGS is lesser than the threshold voltage, that is 1 volt, you will simply get a flat line because there is no current. Right? Now let's assume that your VGS is equal to 2 volt. Then how much would be the current in saturation region? So the expression in saturation region is half mu n COX W by L, which is 100 microampere per volt square, into VGS minus VTH, the whole square. Right? VGS is 2 volt, VTH is 1 volt, so it's basically 1 square. So this gives you 50 microamperes. So I know that I have to draw a flat line for saturation region, which is at 50 microamperes. But I also want to know from what point on VDS I have to start drawing this flat line. Right? So what point would that be? It is in saturation when your VDS is greater than VGS minus VTH. Right? So it has to be greater than VGS minus VTH, and this corresponds to 1 volt in the particular case. So beyond this, so maybe this is, let's say this is 50 microamperes, and beyond 1 volt I have a flat line. Right? And how does the relationship look till then? So the equation for that is this. Is this a linear equation? It's a parabolic equation, right? So what you have, that equation corresponds to a parabola like this. And it turns out the linear region is valid till this point. Right? And beyond this, the saturation region takes over. So you have the parabola coming like this. Now it's called as linear region because if you zoom in and observe for small values of VDS, it looks like a linear line. Now let's quickly plot for VGS equal to 3 volt. Tell me what would be the saturation region current. So half into 100 microamperes into 2 square, right? So this corresponds to 200 microamperes. So I plotted 50 here, so this is 100. You have 200 microamperes, and from what point onwards does saturation region start? From 2 volt, right? So you will have a line like this. Quickly calculate for VGS equal to 4 volt. This is 450 microamperes. So this is 300 micro, 4. My 450 microamperes is somewhere here. And you'll see that the value is valid from 3 volt onwards. So I wanted to show you how the curves are going to get spaced. Even when your VGS is increasing by equal increments, your curves are not at equal spacing, right? And that is because you have a quadratic relationship. And you also see that the point at which the region is shifting from linear to saturation, that is also not constant, right? That depends on VGS, that depends on the value of VGS minus VTH. So if your VGS is changing, the point at which the shift between linear and saturation is happening will also change. So before this, you have the linear region, and after this, you have the saturation region. Okay. So let's do a similar plot here also. I'll not look at the exact current values, but we'll plot for two values of VDS. Let's say I plot for VDS equal to 1.5 volt and VDS equal to 1 volt. So let's start with the 1.5 volt first. How do you expect the curve to look like in the initial regions? So this is I2 versus V1. We're plotting I2 versus V1, that is with respect to VGS. So when your VGS is smaller than the threshold voltage, which is given as 1 volt, you would see that your current is 0, right? Now as VGS crosses 1 volt, what is the region of operation of the transistor? Is it saturation or linear? Why linear? So your VDS is 1.5 volt. Your VGS is 1 volt, slightly more than 1 volt, let's say 1.1 volt. VGS minus VTH is definitely smaller than VDS, right? VDS is greater than VGS minus VTH. So it enters into saturation region, right? So it follows the quadratic relationship. And then at what point does it switch to linear region? At VDS plus VTH, right? So if VDS is 1.5 volt, at 2.5 volt, it makes the switch to linear region. So I will sketch it to 2.5, right? And beyond this, you will have a linear curve. So it is in saturation till here, and then in linear region beyond that. Now let's also plot for VDS equal to 1 volt. So during this region, it remains the same. During the saturation region, does it follow the previous curve or does it have a different trajectory? In the saturation region, is your current a function of VDS? No, right? So it will follow the same curve because the current is not a function of VDS. So it follows the same curve. Till what point does it follow? Till it reaches 2 volt, till it reaches VDS plus VTH. Okay. Now beyond this, it will be in linear region. So then the curve begins to separate out. Right. So this is in saturation. This is in linear region. Okay. Now looking at the 4 plots, and based on our analysis of the large signal characteristics for an ideal amplifier, where do you think we should use this device as an amplifier? Which region? Saturation, right? So what we'll do now is we'll do the derivation of the incremental parameters in both the saturation and the linear region. Then we'll compare Y21 and Y22 and then confirm that this is a reasonable decision to come to. So we are going to look at the incremental network. For the MOSFET in linear region. We'll first list down the EC ones. Y11 is equal to, this is dou Ig divided by dou V1. This is 0 because Ig is a constant 0 throughout. Y12 is dou Ig by dou V2. This is also equal to 0. Right? Now the expression for drain current was mu n COX W by L into VGS minus VTH into VDS minus VDS square by 2. Okay. Y21 given by dou I2 by dou V1, that is same as dou ID by dou VGS. Can you give me the expression for this? So I have to differentiate the expression for ID with respect to VGS. What do I get? Mu n COX W by L. So is it into VGS minus VTH? Into VDS, right? You are differentiating with respect to VGS. Okay. And Y22 given by dou I2 by dou V2. So in our case, this is dou ID by dou VDS. Please give me an expression for this. This is mu n COX W by L. You differentiate the first term, you get minus VDS. Okay. So now when you work with MOSFETs, you don't keep calling it as Y21 and Y22. Instead of Y21, you call this as GM, right? This is also called as the trans conductance. So a conductance relates the voltage and current at the same port. A trans conductance relates the voltage at one port to the current at a different port. Right? So it is conductance of some sort, but trans. So trans conductance. Now Y22 is simply GDS. So now the incremental network looks like this. Y11 is 0, Y12 is 0, therefore nothing is sketched at the first port. In the second port, you have a GM VGS and another GDS. This is your I2 and this is VDS. So this is small signal ID, where the value of GM and GDS are given above. So let's repeat this exercise for a transistor in saturation. What is Y11? 0. Y12? 0. Now Y21, which is same as GM. This is dou ID by dou VGS. And Y22, which we call as GDS, is dou ID by dou VDS. And the expression for the current is half mu n COX W by L into VGS minus VTH the whole square. So please take the derivative and tell me the answer. Y21 is 0. This will be equal to mu n COX W by L into VGS minus VTH. And Y22 is? This is equal to 0. So now the incremental network looks like this. We have VGS here. Y11 and Y12 are 0, so nothing is connected to port 1. Then you have GM times VGS. Anything else? That's it. GDS is also 0, right? So this is your VDS and the current flowing here is ID. So let me quickly summarize the incremental parameters we have seen. So we have seen these values in both saturation region and in linear region. In saturation region, GM was equal to, please look at your notes and read out the answer. Mu n COX W by L into VGS minus VTH. And in linear region, this is equal to mu n COX W by L into VDS. Okay. Expression for GDS. This is 0 here. And here the GDS is W by L VGS minus VTH minus VDS. Let me also remind you the condition for a transistor to be in saturation. Your VDS has to be greater than VGS minus VTH. Now looking at this, which of these GMs do you think is larger? Saturation region, right? Because you have VDS here and you have VGS minus VTH here. For a transistor to be in linear region, which means for this GM to be valid, your VDS has to be smaller than VGS minus VTH, right? So that alone is sufficient to conclude that GM in the saturation region is going to be greater than GM in the triode region, right? Similarly, the GDS in the saturation region is going to be smaller than GDS in the triode region. Now, as your VDS is going from 0 to VGS minus VTH, how does your GM value change? When your VDS is 0, right, what is the value for GM? You'll first have to identify what is the region of operation, whether it is saturation or linear, right? If your VDS is 0, what can be the region of operation? Only linear, right? So you have to look at the GM equation corresponding to the linear region. And what is the value of GM? 0, right? And how high can it go? When your GM is, when your VDS approaches VGS minus VTH, that is when it enters into the saturation region and your value is given by whatever is the GM value in the saturation region. Okay. Similarly, what is the initial value for GDS when your VDS is 0? That will be equal to mu n COX W by L into VGS minus VTH. Does this look similar? This is same as the GM in the saturation region, right? And what is the final value? It goes to 0. So if I were to simply make a plot of this, so I'm plotting it versus VDS. How does your GM look like? It starts from 0 and it will keep increasing linearly with VDS, and it will keep doing this till the value VGS minus VTH. After this, it is a constant. Okay? And your GDS is going to start from the same value, then it will keep decreasing, and then it remains at 0. Okay? So now, based on all of this, where should we operate our transistor in to get a good amplifier? We have to operate it in saturation region. Right? Because you want a larger GM and you want a small a GDS as possible. So now let me quickly connect a source and a load to our amplifier in saturation region, and let us calculate the incremental gain. So I take a source. Let's say this is some RS, and I connect RL here. Okay. And if the transistor is in saturation region, what all do I have to model? Y11 and Y12 are 0, right? I have Y21, which is some GM times VGS, where VGS is between these two terminals. Right? And do I have anything else? No. So now what is your V out? So what is the current flowing through this? That will be GM times Vs, because your VGS is same as Vs. There is no path for the current to flow, therefore the same Vs will appear here. VGS is same as Vs. So you have GM Vs current flowing, that is flowing out of the resistor. This is at 0 volt, which means you will have a negative potential at this side. So your V out will be equal to minus GM times RL into Vs. So I take the Vs to this side, and this is your gain. So now a quick question. Is a transistor an active device or a passive device? Why active? Why passive? It dissipates power. Okay. So let's go back to the fundamental definition we used, right? That was the I1 V1 plus I2 V2 had to be greater than equal to 0 for a passive device. Right? So let me quickly look at the I1 V1 and I2 V2 for this circuit I have sketched. What is the value for I1? I1 is 0, V1 equal to some Vs, right? What is I2? That is GMVS, and V2 is minus GMRL into Vs. Okay, so if I do I1 V1 plus I2 V2, is this positive or negative? This is negative, right? This goes to 0 and this gives you a negative value, right? So now, is it an active device? So a MOSFET is an incrementally active device. If you relate only the incremental voltages and currents, and if you calculate the power according to that, then you see that it is an active device, right? But if you were to look at the full voltage and the full current, right? So the full voltage will be some Ig plus the small signal current into some VGS plus the small signal VGS plus there is some drain current plus a small signal fluctuation around it, and there is some VDS plus a small signal VDS. Then you will see that of course the first term still goes to 0, but this will be positive. So earlier we got the power to be negative because your VDS was negative, right? But you'll see that your VDS is going to be much large and positive compared to this VDS, right? So overall this term is still going to be positive. So if you look at MOSFET in the full absolute voltages and absolute current picture, it is still a passive device, right? But if you are analyzing it only at an incremental level, then it is an incrementally active device. Is that clear? Now you see that we'll be using this term GM quite a lot. So it's good to have multiple equations available for GM, because depending on what properties are available for you to calculate, whether the bias current is available or mu n COX, W by L is available, etc., it's good to have multiple equations to calculate the GM. So let us derive the other possible equations for GM. So the equation you know now is mu n COX W by L into VGS minus VTH. That's it, right? There is no whole square, right? Can you replace this mu n COX W by L based on the current equation? So you have mu n COX W by L here. You also have the same factor here. Please replace it and give me another expression for GM. 2ID by. So mu n COX W by L can be written as 2ID divided by VGS minus VTH the whole square into VGS minus VTH. So the second expression that you can use for GM is simply 2ID by VGS minus VTH. So now in the same expression, instead of replacing mu n COX W by L, replace VGS minus VTH. What do you get? Yeah. So this would be root of, I'm simply finding an expression for VGS minus VTH, 2ID by mu n COX W by L. This into mu n COX W by L. Okay. So this gives you 2ID into mu n COX W by L. So you have three expressions. So please take a minute and see if you have any doubts in the portions covered so far. I'll end the lecture here.